Everyone. My name is Vu Wun.
Hello, my name is Jonathan Bergston.
Hello, my name is Elvin Petrola.
And my name is Benny Santiago.
This is our entry to the Vertical Flight Society's 42nd Annual Student Design Competition and also our senior capstone. This year, the objective is to design a hydrogen-powered aircraft, hydrogen electric-powered vertical takeoff and landing aircraft for the purpose of observing alligators. The design competition should focus on minimizing carbon emissions from fossil fuel energy sources. There are a couple of requirements that our aircraft have to meet. Some of them are maximizing cruise endurance at 30 meters above sea level in order to enable the effective environmental surveillance of these alligators.
So going over the specific mission profile, you can see under mission requirement that the mission profile is really broken up into 5 sections. There's the takeoff section, then arriving to the river, and then the main portion that Vu mentioned, the endurance section at the river at 30 meters above sea level, and then returning to the Wright Brothers Memorial, which was the starting point, and then landing.
So in order to design this aircraft, we had to consider some specific design criteria. The most important design criteria for us was endurance, hover performance, and climb speed in that order. So for endurance, we weighted that in our weighted Pew matrix as 20% importance, hover performance at 14%, climb speed at 7%. This is because segment 9 in our RFP, which is our list of requirements, is to maximize our endurance range or endurance time. Endurance is essentially how long an aircraft can fly. Next is our hover performance. Since we have to be in the air around a certain area for an extended period of time, we consider that pretty important. And then finally, climb speed. As part of the RFP, there's a requirement to match certain specific climb speeds. So our aircraft had to meet these minimum requirements in order to perform.
To meet the mission statement, we had to start off with a traditional studies, and we went with a conventional helicopter that consists of fentrons, 3 blades, and a streamlined fuselage. With looking at our specifications, we went with the fuselage length of 10.5 meters, and with a main rotor chord of 0.18 meters, along with the rotor radius with 4.1, and as our tail rotor chord and radius, they were 0.02 meters and 0.472. And the reason why we went with the conventional is because it's very beneficial for its hover efficiency, and there's a lot of information through research papers and online that it's better off to go with to meet the mission statement.
Right. And the way we further decided to address the RFP was through our 4 main characteristics of our aircraft, specifically the motor selection, the fuel tank sizing, the maximum number of passengers, as well as the fuel cell stack selection. Right. So for the motor, we decided to go with the HP DM250 due to the fact that it has a very high peak power of 335 horsepower, but also has a very low weight in comparison to other motors that we have considered. In relation to our fuel tank itself, we decided to go with a graphite epoxy material with a total volume of 0.38 meters cubed, right? For this design itself, we went for a fairly strong material design that can also has a very low weight as well as about 28.5 kilograms. And through the design itself, we managed to essentially have a hydrogen capacity of about 6 kilograms per tank. And the way this works is that it allows us to have a very optimal loiter performance at section 9, as mentioned previously. And through that, we are able to have about 2.5 hours of flight time. And beyond that, our Proteum stack is essentially chosen with a number of 520 fuel cells and with the dimensions of about essentially 1 meter cubed volume, right? So for this one, the way we decided to go about it is to ensure that we had sufficient fuel cells to provide sufficient power for the overall flight, which is shown within our power consumption diagram, right? where we're able to show that for certain aspects of the flight, for example, hover and vertical climb, we're reaching to a maximum of about 190 horsepower required. So by having 520 fuel cells, we're able to reach about a maximum output of 210 horsepower, thus meeting the power requirements needed for both hover and vertical flight, which is our highest power requirements. Beyond that, we do have a few forward flight requirements of 95 and 96 horsepower, respectively, for loitering cruise. Of course, these are done at our best endurance speed, which is approximately 45 knots.
To meet the power requirement and the mission, there were a total of 5 candidates, 5 airfoils, including the OA 209, OA 212, and the Sikorsky 1095, and the NACA 2414, and also the VR 15. They were all analyzed using Expo at a Reynolds of 1 million and Mach of 0.1. With these performance, they reevaluated across a angle of attack from -5 through 18. And pretty much just a comparison from all these airfoils, that the performance is that the NACA 2412 showed a highest CL to drag ratio, followed by the 08 209, the 212, and the Sikorsky 1095, and along with the VR 15. While the NACA 2412 does have a maximum coefficient, which is near the 14 degrees for all airfoils. The reason our team decided to go with the 0212 is because it consists of a low pitching moment, which that's beneficial for reducing the blade torsion, moments, and vibration, and it's also has a ideal high CL max compared to the airfoils. And along with that, that airfoil it's very tailored to helicopter stuff, whereas the 2412 it's more of a generic or a first generations of airfoils. And I could pass the mic to John, where he could discuss about the tail rotor selection.
Yeah. So just like for the main rotor, we wanted to select the most efficient airfoil for the tail rotor, because ultimately the efficiency is kind of the main point we're going after here. And so we looked to a NASA Army research partnership, where for low-speed helicopters, a specific tail rotor airfoil, the RC4-10, was very optimal, and so we went with that. And combining that with the Fenestron, where like looking back at the specifications, we have a much smaller tail rotor radius than a conventional tail rotor would have, and so we're just kind of maximizing our efficiency here with the tail rotor as well.
All right, that's pretty much it. Thank you, everyone, and have a nice day.
Thank you.
Thank you.
Thank you.